This video is a follow-up to the lab that we discussed last class. In our discussion, we established that temperature change does not always indicate the amount of energy transferred. First, we looked at the the temperature change of two objects with the same mass, and we found that when the mass was the same, the hot and cold water had the same amount of temperature change, hot cooling down and cold heating up by the same amount. But we found that mass does make a difference. When we use twice as much cold water, the temperature of the cold water changed half as much, because we reasoned that when the hot water particles gave energy to the cold water particles, twice as many particles had to be sped up. Therefore, each particle did not change speed as much, because the energy had to be distributed over twice as many particles. So we had concluded that energy so far, first off, it's transferred between two objects, and we don't gain or lose any when we have an insulated system, as we did with the foam cups. And second, it seems like mass has an effect upon temperature and temperature change and energy. So when we look at this picture here, I want you to think about, we've got 4 samples, A, B, C, and D. And the best thing that you could do for yourself right now is to pause. And before I go through and explain all the answers, try to answer the questions for yourself. That's how I would be handling this with everyone who is in class. So if you go through that process of thinking about it first, then you are going to understand the answers better. All right, hopefully you took my recommendation and paused. Now I'm going to explain each of them. We're comparing everything back to situation A. So the first question asks us to compare the amount of energy transferred in B to the amount of energy transferred in A. I noticed they both have the same temperature change, but there's twice as much mass in B. So if the mass is twice as big, that should require twice as much energy to achieve a 10 degrees Celsius temperature change. In the second question, we are asked to compare situation C to situation A. I noticed that in this case, the masses are the same, so we're trying to heat up the same number of particles. This time, the temperature change, the delta T, is what the difference is. The change in temperature is 3 times bigger in C. Well, if we have to make the particles get 3 times faster, then or speed them up 3 times as much, it's going to take 3 times as much energy. The third scenario is to compare situation D to situation A. And I noticed 2 changes this time. This time the mass is 2 times bigger, and the temperature change is 3 times bigger. I usually hear one of 2 answers. I will hear people say the energy required is 5 times bigger, and I will hear the energy required is 6 times bigger. In all these cases, we've been talking about really multiplication and proportionality. So if we have 2 times as many particles, and every particle's got to get 3 times, sped up 3 times as much, then we're talking about 2 times and 3 times bigger. That's going to give us a total of 6 times as much energy required. So where we left off last week and where we're kind of reviewing today is that so far we know that thermal energy does not just depend on temperature change. It depends on mass that's being heated up or cooled down, and on change in temperature. We also had just begun talking about trial 3 in our lab. And in trial 3 in the lab, you put room temperature metal into hot water. And we looked at the temperature change of the metal and the hot water. And that seemed, there wasn't as clear of a pattern as the first 2 trials, but we noticed that it definitely seemed like for every metal, The water temperature change was very small compared to the temperature change of the metal. And we talked about it must have had something to do with the fact that we're using metal now instead of water, but each metal seemed to be giving different results as well. So in addition to thermal energy depending on mass and change in temperature, this leads us to believe it might also depend on the type of substance that is being heated up or cooled down. I had students say things like, it seems like the metal stores a different amount of energy. And I even had one person say the metal has a different capacity for storing heat. So that's actually exactly what we call this quantity that describes how different substances store different amounts of energy. So we define a constant. It's constant for each type of substance, but different for different types of substances. It's called the heat capacity. Heat capacity is the amount of energy for every 1 gram of a substance to be increased in temperature by 1 degree Celsius. So one heat capacity that you'll probably memorize, although I will give it to you on the test, is the heat capacity of water. It's very common. The heat capacity of water is 4.18 joules for 1 gram of water to go up 1 degree Celsius. And this is the first time that this letter J has come up. J is called a joule, and it is the unit for measuring how much energy, the unit of energy. In fact, here in the United States, if you read food wrappers, we have energy quantified in amounts of calories. In Europe, if you get a food package and you look at the nutrition facts, you'll actually see it listed as energy, and it'll be given in units of kilojoules instead of units of calories. So around the world, besides here, we even measure the amount of food energy we take in by consuming food in these units of joules. So this means that it takes 4.18 joules to heat a gram of water up 1 degree Celsius. The heat capacity of water is actually extremely high. Most substances heat up faster than water. And we did talk last week about the idea that if you put a pot on the stove and then you put water on a stove, the pot changes temperature much, much faster because it's made of metal. It doesn't take long at all for the pot to get up to temperature. The water, on the other hand, takes many minutes to get up to the temperature that you want. And so that gives us an indication that the heat capacity for the pot is different, that it takes less energy to heat the pot up 1 degree Celsius or many degrees Celsius. So as I just wrote down, and I would recommend you write in your notes, different substances have different heat capacities. And so we're going to use some lab data. In fact, I just pulled some lab data from several teams' boards, teams where I could tell what metal they had actually tested. And we're going to look at that data and we won't be able to calculate the heat capacity for them, but we can rank aluminum, copper, and lead and see how their heat capacities compare to one another and to the heat capacity of water. So before I talk about this data, I just want to establish how we're going to think about it. We know that for trial 3, we used the same mass of water and our metal. So mass isn't going to be a factor here. That in this case is the same. We also know, because we used an insulated system, that there was the same quantity of energy exchange. The water lost the energy and the metal gained the energy, but the amount, the absolute value of that amount of energy was the same for both our metal and our water. So, and we also know now that they have different heat capacity, different capacity for storing energy because they're different substances. So if they got the same amount of energy, when something changed temperature more, it means that it does not take as much energy for each degree Celsius. I'm going to say that again, because something changed temperature more when it got the same amount of energy. That means that it takes less joules for each change in degrees Celsius. So I said that twice and then I wrote it down. If the change in temperature is larger, like it is for all of our metals, then it must take less energy for that metal to change 1 degree Celsius than in comparison to the water. And that matches our experience I just described with pots heating up faster. They don't have to sit on the stove as long as water does to heat up and go through the same temperature change. So what I did when I looked at these outtakes of different boards is I did a little ratio of temperature changes, and I thought, well, if the temperature change is smaller, the heat capacity's got to be proportionally bigger. So I thought about it as the temperature change of the water compared to the temperature change of the metal would tell us what percent of the heat capacity of water that metal has. So for every 2.6 degrees temperature change for water, aluminum changed 9.4 degrees. So that tells me aluminum's heat capacity has to be, or could be around 28% that of water. Now, I'm not sure that's exactly going to be perfect, but we're just trying to rank here aluminum, copper, and lead, or compare them. I found 2 different teams' data for copper, and I again compared the water temperature change to the metal temperature change, and they're, for 2 different teams, pretty similar ratio of water temperature change to copper temperature change, and I got 19% and 17%. And that suggests that copper's heat capacity must be smaller than aluminum's heat capacity. And then I noticed that lead had the biggest temperature changes of all the data that we looked at, like 27 degrees, 22 degrees, and for tiny water temperature changes. So that tells me lead, we're buying there's so many joules or temperature change that's resulting here that it must not take much energy at all for lead to change 1 degree Celsius. The percentages I calculate here, 10, 7, 4, all by far the smallest. So based on this data, if we were to rank what we predict the heat capacities are going to be, I would say that aluminum has the greatest heat capacity of the 3 metals we looked at, and then copper. And finally, lead, which our data suggests has the smallest heat capacity. I would encourage you to do a quick Google search and see how our data matched up. And you can go ahead and, based on this video, you should be able to finish all the questions remaining on your lab sheet. If you have some questions for me based on what was discussed in this video, write that down on your lab sheet so that you can ask me when you're back in class with us later this week.